Just keep on complaining. All right. So a very special section of related rates is cones. Okay, so you should all be very. You only get to live through this once. All right, so enjoy it. Okay.
I know how to do it.
You know how to do it.
Yeah, you have to set 2 equals pi of 16 times 5.
What's up, Naomi? It's not really new. It's just a new shape. That's all. It's all the same idea.
Okay, well, I don't know anything about
Okay.
besides that.
Listen. Just stick with me here. Look. We have a conical tank. Okay? A conical tank. Okay? It's a cone-shaped tank. We're filling it with water or something in this case. I don't know, but we're dumping in some stuff. Okay? As it gets dumped in, you can imagine that there will be stuff in there being filled up. Yes?
Yes.
Okay. Okay. Yes, it is. All right. Key things to keep in mind here. Look, number one, the conical tank itself is not changing. All right? The dimensions of the tank are not changing. What's changing are the dimensions of the water inside of the tank. It's getting filled up. Okay? As it's getting filled, what shape is the water going to have?
A triangle.
It's not it's a cone. It's three-dimensional. It looks like a triangle on my paper, but it's a cone. Okay? And they're always going to ask you about how fast like the depth is changing, or how fast the radius is changing, or how fast the volume is changing. Okay? Those are the three big variables in this, right, Judy? Okay. So, when they tell us it's being filled at 2 cubic meters per minute, what variable is that? If it's not volume, it's 2 cubic meters per minute. It's change in volume.
It's a change in volume.
It's the change in volume, which we write as,
DVDT.
that's dVdt. dVdt, that's the volume of water in the tank, is changing at 2 cubic meters a minute. Okay. So, I want to know how fast the water level's rising. Well, this is the water level right here. So how fast it's rising is really saying how fast is this depth changing. I'm going to call that h. They want to know how fast that's changing. I'm going to write that as dH dt. I want to know what that is. Okay? So we need some equation that links volume to height, to h.
So pi equals 1/3 pi r.
Volume is 1/3 pi r squared h. Okay? Now, the problem with this right off the bat, and most cone problems have, not all, but most have this problem, is that when we derive this the way it is, we're going to get a dv dt, we're going to get a dr dt, and we're going to get a dH dt. Which one of those do we not want? We don't want dr dt because we don't know it and we're not being asked about it. Okay? So we'd also have to do the product rule in this case, if you're thinking about that. All right? But that's not really a problem. It's just something you got to remember. All right? So typically cone problems, when you're filling a tank, have an extra equation we're going to use because we don't want r to be in there. So we want to get rid of r, which means we need another equation so we can sub out r.
Surface area.
It's not surface area. It's this. Look at this.
Circumference.
4/16 equals r in.
Area.
Yo, do you see that this big triangle here must be similar
To the smaller one.
to this one? That's like our shadow triangle turned sideways. Okay? They're similar, which means their sides must be proportional. Which means even though the height and the radius of the water, which we haven't even labeled yet, which is bad of me, that's the radius of the water right there, okay? That's a little r in this equation. They're changing, but they have a relationship with each other. Oh, it's right on the board behind me. That makes sense. Okay. So, keeping in mind here, it says it's 4 meters? 4 meter radius, okay? And a 16 meter height. Those numbers are not changing. All right? So please, you you're not going to plug those into your volume equation. That doesn't make any sense. That's not the volume of the water. The volume of the water, you need the dimensions of the water that's in there. Okay? We only use these numbers because that's going to allow us to get our similar triangles. And we know that 4 over 16 has to be the same thing as R over H. Okay? And that allows us to solve for R because we want to get rid of it. So R is 1/4 H. Everybody okay with that?
Oh, okay.
And because of that, we can rewrite our volume equation like this. Cool. Now there's no R, and now we're just going to simplify it down. So volume is going to be 1/3 pi times 1 over 16 h cubed, which looks a little complicated. So let's put our fractions all together here. That's the same thing as pi over 48 h cubed. And that's simplified down an awful lot. This is going to be easy to derive. Now we're basically done. We're going to derive it and plug in and solve. Okay? So when we derive the left side, we're going to get dv dt is equal to, we're going to multiply by 3, but that's going to cancel with the 48 and make a 16. Okay? And then we're going to have h squared dh dt. Cool. And now we're just going to plug in everything we're supposed to know here. So dv dt, they told us was 2. Pi over 16 is just kind of there hanging out. They told us specifically how fast is the height changing when its depth is 5. So that means h is 5. Okay, which means h squared is 25. And then we're going to get dh dt here. And then because I want to solve for dh dt, we're going to multiply by 16 and divide by 25 pi. So that is 32 over 25 pi. And the units on the height, since volume was in cubic meters, then the units on the height are just meters. So this is going to be meters per minute. And that's just a measure of how fast the water level is rising as we fill it, okay? Now, let's think about this here real quick. So that's the end of this problem. That's true. But let's think about this. What should happen if we're filling this thing at a constant rate? Okay, don't yell us out at me. I want you to think about this here. Let's time this.